I'm William Barucki, the principal investigator of the Kepler mission, and today I have the privilege of announcing the discovery of Kepler's first planet in the habitable zone of a Sun-like star, Kepler-22b. It's 2.4 times the size of the Earth. It's in an orbital period of 290 days, a little bit shorter than that of the Earth. It's a little bit closer to its star than Earth is to the Sun, about 15% closer. But the star is a little bit dimmer. It's a little bit lower in temperature, 220 degrees lower in temperature. It's a little bit smaller. So that means that that planet, Kepler-22b, has a rather similar temperature to that of the Earth. The Earth's radiative temperature that Natalie mentioned is 255 degrees Kelvin. This is 262 degrees Kelvin, some 7 degrees different. So if the greenhouse warming were similar on this planet and had a surface, its surface temperature would be something like 72 Fahrenheit, a very pleasant temperature here on Earth. The star is some 600 light years away, so it's not terribly far away, but not terribly close either. You can see the images here. The orbital periods are about the same size. You can see the star at the top is a little bit dimmer than the star at the bottom of the Sun. And you can see how the Earth compares to Kepler-22b. What I'd like to talk about next is the data that made this discovery possible. Could I have the next figure? What we see at the top here is the Kepler's light curve. And the light curve is simply the brightness of the star as a function of time. So you see the variation of the brightness of that over 700 days of observations. Now, much of the drifts and jumps and things like that are due to the measurement errors that we have, and we need to take that out, correct the drifts, correct the jumps, and what our analysis pipeline does is produce the curve below it. If, on the other hand, we start and we look at the upper curve, you see there's three triangles. The three triangles are pointing out where the three transits that are required for confirmation occurred. And if you look, you can't really see the first event. The second event is that tiny little tick. The third event is another tiny little tick. And so it's nearly impossible to see that by eye unless somebody tells you. But when you take the data and you put it through the data analysis pipeline, what you end up with is that lower panel, and it's very clear. The transits are marked. They're very, very clear here. We've magnified the observations. The black areas are areas where the spacecraft did not take data. It turned toward the Earth, sent the data back to us, and a large one to the right-hand side is where the spacecraft was in safe mode, again, not taking data. But what's special here, what's really special, is to notice the first triangle occurs just a few days after we leave commissioning and we go into science operations. So we picked up the first of the three necessary transits. The second one is pretty obvious. The third one occurs just before this period of about 2 weeks where the spacecraft was not taking data again. It was in safe mode. That occurred just before Christmas of 2010. And we had this wonderful fortune then to find these three transits where, had there been any change when they occurred, we would have missed them. We would not be declaring the Kepler-22 as our first planet in the habitable zone. So it's a great gift, and we consider this sort of our Christmas planet. So let's go on to the next figure. Here we've taken those three transits. We've added them together so you can really clearly see that transit. So you see the dip. You see how well it's defined. The depth of that dip is telling you the size of the planet. The size of the planet is 2.4 radius of the Earth. It's not 2.5, it's not 2.6, it's 2.4, just a smidgen above and below that. The period is something like 7.4 hours, and what's especially interesting are the dots above that. The dots above that are measurements we took not when the transit's occurring, but half an orbital period later. And that's the time where the planet's not going in front of the star, it's going behind the star. And so, since the planet typically it gives off about 1/1000th the light of a star, you shouldn't see any difference, and you don't see any difference. If you saw a decrease, it would mean it wasn't a planet that we were seeing, it was a star, because its light would be occulted. So, great confirmation, it's a planet, not a little star. On the right-hand side is another independent measurement. This is done by the Spitzer Telescope, which is also in orbit around the Sun, like the Kepler telescope. But the Spitzer Telescope looks in the infrared portion of the spectrum. Kepler looks in the visible portion. And if it's a planet, the depths of both transits should be essentially the same with an experimental error. And if we look, we see they are. The white curve is the curve from Spitzer, the red curve, that from Kepler. And the agreement is beautiful compared to the measurement error. So another wonderful confirmation. It is a planet. It is not some other astrophysical phenomenon. Could I have the next figure, please? What we're going to talk about here is what we'd like to be able to get at is the composition of this planet. To get a clue of the composition, you need the size and you need the density. The density you get from the size and a measurement of the mass. We don't yet have a measurement of the mass. Kepler measures size, not mass. But with our colleagues, we can sometimes get the mass with ground-based measurements. So let's look at what we have, what we can learn from what we have at currently. Vertical axis is the size of the planet relative to the size of the Earth. The horizontal axis is the mass that we measure for that planet. Lower left, we see Earth and Venus. Upper right, we see Uranus and Neptune, two of the larger planets in our solar system. And then we see we see a yellow band, which represents the size of Kepler-22b, but we don't know where Kepler-22b lies on that band because we don't have the mass yet. But when we look at the other curves, we see the white curve that goes from the Earth up to the right. And that is, if you took more rocks, more material that Earth is made out of, and you kept adding it to the Earth would grow in size, it would grow in mass, and would follow along that curve. If instead we had a planet that was essentially water and ice, that would be the dashed curve. And its density is less, so it's above the curve of Earth, which is mostly rock and iron. And so we would see it grow, and it would cross that yellow curve, the yellow band for Kepler-22, as it got more and more mass toward the mass of 20. If we talked about planets that had lots of hydrogen and helium, when you add those gases, they're very expansive, and so the atmosphere becomes very large, and we see planets like Uranus and Neptune. So 10% hydrogen helium, the lower white curve, solid curve. 20%, a curve somewhat above Uranus and Neptune. It's clear from the yellow band that's not where Kepler-22 lies. It lies somewhere between Earth composition, so you would expect it to have a lot of rocky material, and it probably has a lot of water as well. This coming summer, we will have an opportunity to try to measure that mass, because the star will be high in the sky, and the telescopes, the ground-based telescopes like Keck and possibly HARPS North, will be able to at least attempt to get the mass of this planet. And I believe they have a good chance of being successful, and they will know where this planet lies on that curve. Clearly it lies in an area which hasn't been explored. We have no planets like this in our solar system, things that lie between the Earth and Uranus and Neptune. So that will be a wonderful part of our discovery.